Our first attribution method is ablation analysis. It answers a local counterfactual question. Given a transition from a source configuration to a target configuration that improved performance, how do we decompose that improvement across the individual hyperparameters that changed? Recall the formulation from chapter 3, following faucet and hose. We fixed the source configuration, typically the default configuration, and the target one, typically the incumbent returned by HPO. They differ in some subsets of hyperparameters, and ablation attributes the performance gap between them to those hyperparameters. The construction is an ablation path, a sequence of intermediate configurations obtained by flipping hyperparameters from their source to their target values one at a time. At each step, the flip is chosen greedily to maximize the immediate improvement, and the realized gain, delta I, is credited to the hyperparameter that was switched. The result is a local path-based importance ranking. The cost is that a faithful path requires many genuine evaluations of the cost function, informative but potentially expensive. Biedenkopf et al. Make this essentially free. The observation is that the surrogate-based optimizer, say SMAC, already fits a random forest surrogate approximating the cost over the configuration space as part of its Bayesian optimization loop. The information needed for ablation is therefore already latent in the run. Model-based ablation replaces the real evaluations along the path with surrogate predictions. Given a fitted surrogate, the analysis carries negligible marginal cost. 3 consequences: no computation beyond the HPO run, smoother, lower variance importance estimates since the surrogate regularizes the response, and clean integration into existing surrogate-based pipelines. We obtain the same ablation path but via cheap surrogate queries rather than expensive black box evaluations. Let's have a look at the algorithm. So first of all, we have as inputs the source configuration and the target configuration, and of course the surrogate model. Initialize then the current configuration to be the source, and let S be the set of hyperparameters on which the source and the target disagree. Then iterate while S is non-empty. For each hyperparameter I still in S, construct the candidate that sets dimension I of the current configuration to its target value. Select I star maximizing the predicted improvement, so lowering the cost, the surrogate at the current configuration minus the surrogate at the candidate. Record that difference as delta I star, commit the switch, and remove I star from S. On termination, you return the ordered sequence of hyperparameters with their attributed gains. Let's have a look at a concrete instance. Each row reports a hyperparameter, its source to target value change, its position in the greedy order, and the attributed accuracy gain. Here, learning rate is switched first and dominates, contributing 3 points of accuracy or 3 points of reduction in the cost, followed by max depth, subsample, reg lambda, and finally n estimators, whose marginal contribution is negligible. The interpretation is a defensible local statement. For this run and this source target pair, the learning rate is the dominant driver of the improvement. This is precisely the kind of concrete attribution one can report to a stakeholder. However, this is to be seen with the caveats we turn to next. 2 further structural limitations. First, locality. The path connects one specific source to one specific target, so the estimates characterize behavior only in the neighborhood of the path. They do not generalize to the configuration space at large. This is a fundamentally local explanation. Second, it's path dependent. So the greedy choice at step K determines which hyperparameters remain and the context in which they are subsequently evaluated. Different type breaking, different starting points, or randomized path enumeration can therefore yield different attributions for the identical source target pair. Averaging over randomized paths mitigates the variance, but reintroduces the evaluation cost that model-based ablation was designed to eliminate. To summarize, ablation attributes a performance change to individual hyperparameters along a transition from a baseline to a configuration of interest. Model-based ablation reuses the optimizer's surrogate to compute these paths at negligible extra cost, yielding a local ordered importance ranking. But but the scores are local and path dependent, valid only for the specific source target pair and sensitive to the greedy order. And interactions are not modeled at all, so interacting hyperparameters are systematically over or undercredited depending on the switch order.